Hello YouTube. It's been quite a long semester, definitely a lot changing in the world, but I'm here now and so are you, and hope you're excited to explore some new math. And so this is something, this topic is something many of you may have heard of before, but may not exactly know sort of what the larger significance or sort of where it comes from, what it means. And as per usual, I like to consider how looking at different perspectives will give us a much fuller appreciation for the true beauty of our subject matter, in this case, mathematics. So I think by way of introduction, I will ask you a question. What is the most irrational number? So the most irrational number. Right, okay. How do we go about this? Well, why don't we just sort of first think about numbers we know and can go from there. So you're probably familiar with good old pi, right? So we know that pi is approximately 3.14159. And so what we can write this then is it's going to be 3, right, plus some fraction of 1, right? This sort of 0.14159. So what we can do is take the reciprocal of this bit, 14159, and end up with 7 point something something something. And I can then do the same process, subtract that 7, and I'll end up with 1/15. And so essentially I can continuously write out what pi is, sort of in this, like, little descending fractional thing over here. So this obviously sort of continues on forever because pi is irrational. However, if we were to just stop it at this point, I think many people would agree we have a pretty good approximation, right? Because this is 3 1/7, also known as 22/7, right? 3.14 is a pretty good approximation for pi. And if you think about it, this number 7 is actually pretty big, right? 1/7 is, I mean, it's something, right? It's not huge, but it's something. And obviously, the larger than this number the denominator becomes, the closer this fraction gets to 0. In other words, the more easily we can approximate whatever irrational we have. So if we were to look, for example, square root of 2, it's about, okay, 1.4142, something like that, right? If we do the same thing, it's going to be 1, okay, plus this fraction. Take this little bit, get the reciprocal of that, you're going to get 2. Again, if you subtract 2 and then take the reciprocal of that, you're going to get this same thing. So you're essentially going to get this repeating pattern all the way down. And now, obviously, 2 is less than 7, so it's going to be a bit harder to approximate. So this is definitely square root of 2 is definitely more irrational than pi is, because this number is getting smaller and smaller and smaller. Okay. It's going to be less easy to approximate. However, what if we want the most irrational? In other words, we want the smallest integer we can have in place of 2. In other words, we want a number such that we have 1 plus 1 over 1 plus 1 over 1 plus etc., etc. This repeating fraction. So, because this is going to give us the smallest number, it's going to be the least hard, the most difficult to approximate at any point, because you don't have a big number that's going to give you a nice, definite, a nice, definite approximation. Because when we do this, right, we have our number, we subtract this 1, take the reciprocal of that, we're still left with more, right? It just keeps repeating like that. We don't have a nice approximation for it. Well, okay, so how do we, okay, so if this is, if I'm saying this is the most irrational number, how do we solve that? How do we quantify it, right? It's repeating indefinitely. Well, if I said this is equal to x, right? How does it help us? Well, notice, since it's repeating indefinitely, this is also x. 1 plus 1 over 1 plus 1 over 1 plus 1 over, etc., etc. So this expression I can rewrite as x equals 1 plus 1 over x, okay? Which is definitely a much nicer equation to sort of wrap our brains around. So if I just go ahead and multiply both sides by x, subtract it over, I get x squared minus x minus 1. Okay, and this is a very nice quadratic that we can factor. Actually, we can't factor, but we can apply the quadratic formula. And therefore, I can say that x is going to be negative b, so 1 plus or minus the square root 1 minus 4 ac over 2a. And in other words, I'm just going to bring this up here. Our x is 1 plus or minus the square root of 5 over 2. So that is the most irrational number. You know, but what is this? Well, if you are familiar with, well, if you go on a calculator and put in 1 plus square root of 5 over 2, you'll get something looks like this: 1.6180339, etc., etc. And this, we say, is phi, the golden number, the golden ratio, right? So phi, the golden number, the golden ratio, golden mean, is the most irrational number. Which is pretty interesting, pretty cool, right? So obviously then, what I want to sort of explore more is this topic, right, of what is the golden number, sort of what is really significant about it. I mean, it is this magnificence of mathematics. And you might say, okay, what about this minus, right? If we had 1 minus square root of 5 over 2, well, you'd get essentially the negative reciprocal of this being negative 0.6180339, etc., etc. Yeah. And that is also technically the golden number. And if we take the absolute value of that and just get sort of subtract 1 from this, this also is familiar as the golden mean. So they're all very much related. But so that's, I think, a pretty interesting way to introduce this idea of, okay, what is the golden number, right? Why does it matter? And I think, I mean, definitely, given the fact that it is the most irrational number, sort of this in our abstract number system, is quite fascinating. And especially it's just amazing, we can sort of quantify this sort of infinite fraction. Brilliant. Okay. Now, okay. Sort of switch gears from our abstract number theory land. And to look, and now let's look at something a bit more concrete. Let's look at a geometry problem from Euclid's geometry. So say I have a line, right? Some line segment. And I divide it into two parts, A and B. So I have some line segment divided into A and B. Okay, well I want to find the ratio. I want to have A plus B over A. I want to say that that is equivalent, right, to A over B. I want to say that A plus B over A is equivalent to A over B. So as I have this ratio, this equivalence of ratios, and I'm going to call this phi. Okay, so what I can do is if I go ahead and solve this, I know this is going to be 1 plus B over A equals A over B. Because I know that A over B I'm saying is phi, this ratio, right? What I'm going to have is 1 plus 1 over phi equals phi. And this looks very familiar from what we were doing just before, right? We're going to get, if we multiply by phi, then move everything over to one side, we're going to get phi squared minus phi minus 1 equals 0. And if we solve this again, we're going to get that phi is, again, 1 plus minus the square root of 5 over 2, which is what we said before. So in other words, a geometric way to think about the golden ratio, as that's where we get the term ratio, right, is such that satisfies this, this series of equivalences with this line segment. So that's sort of the idea of where the golden ratio comes from. And what's really cool about this is sort of applying this, we can sort of apply this, this idea of geometric ratios and create something that's pretty cool. So, what we can do essentially is draw a golden rectangle. And again, anything with the word golden in this context is going to mean relating to 1.618. Okay, golden rectangle, right? And what this will be called is Sectio Aurea, literally the golden section, golden mean golden area, or the divina proporzione, right, divine proportion, by Luca Pacioli and Leonardo da Vinci, right? And so what's sort of cool about this is if I have this golden rectangle, right, sort of doing the same idea where I have sort of this side of, I have this sort of side A, length A, length B, length A. What I can do is divide this golden rectangle into a square and a rectangle. Because this rectangle is actually another golden rectangle. So if I come down here, again I sort of break it down into a square of length B, and then another rectangle, except again, this is a golden rectangle. So I can then again sort of divide this guy, trying to be as precise as I can in my little measurements, into a square and a rectangle, except again, it's a golden rectangle. And so then again, going to divide this. Eventually we get these two little squares. Except if I can actually draw squares. Yeah. So essentially, I can take any golden rectangle and divide it into these constituent parts of a square plus another golden rectangle. Divide that into a square plus another golden rectangle. Divide that into a square plus another golden rectangle. Divide that into a square plus another golden rectangle. So sort of this fractal beauty. And what we can do essentially is create this spiral. Sort of poorly drawn, but we can create a spiral that goes within our golden rectangle. And this again, sort of, we can name the golden spiral. Also, there's another name that we'll cover in a second. But what's cool about this is, sort of, okay, we sort of started with this sort of abstract, number theory. Okay, find the most irrational number. Okay, it turns out to be the golden number, right? 1.618033987, blah 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 blah. Okay, then we looked at this problem from Euclid's geometry. Okay, well, what if I have a line segment and I have length A, length B, and I want the ratio of the sum of the sides, of the sum of the length over this first length to be equivalent to this side over that side. And so then I solve that again, and we get this interesting ratio, 1.6180339, etc., etc. And then what we can do is we can create these rectangles based on these ratios, and then we can sort of divide them again into this sort of square piece, and then we get another golden rectangle sort of twisting like that. And sort of connecting these all, we can sort of get this spiral. This sort of almost like logarithmic spiral, but that's going to correspond to that ratio, which we said, right, was 1.6180339, which is just amazing, right? Just beautiful. And so, as I sort of alluded earlier, sort of the idea of the Sectio Aurea, the divina proporzione, this sort of, you get this idea during the Renaissance. Sort of this explosion of culture and of learning and of mathematics, and sort of rediscovery of Greek ideas, and obviously, so I mentioned Euclid. So it's kind of interesting is out of that period we get this idea that that the universe is sort of it's that our universe is a mathematical one, that things aren't just sort of random, nor are they ordained by God per se, but rather, if there is a God, then that God has sort of set up this this universe almost like a deist perspective, sort of set up this universe that sort of runs like clockwork according to mathematical laws that we humans can discover and learn and utilize. And so it's interesting is that this ratio, again, of about 1.6180339, etc., most irrational, right, has been found in many different places. I mean, sort of the common image you might throw up is, oh, take Africa, plop it up here, oh look, it's going to fit in the golden spiral, or look at this galaxy, it's going to fit in this golden spiral. Or look at the pyramids, the ratio of the their base length to their height is going to approximately reach this ratio of 1.6180339.8. An interesting recent study by Johns Hopkins actually revealed that the shape of a mammal skull is actually correlated in terms of their species development to the golden ratio. So in other words, as you move up sort of the evolutionary hierarchy, you get more and more complex creatures, right? They have more and more complex brains, so they're capable of more and more greater levels of higher order cognition. Essentially, their brain shape better approximates this golden spiral, sort of that golden number. And of course, also sort of the common image to sort of look at human face and then sort of take the gold and show how the golden spiral sort of fits into idealized conceptions of beauty. And again, this sort of brings us back to Leonardo da Vinci and Luca Pacioli in terms of looking at the human body as sort of in the Renaissance, in the Enlightenment, as sort of the pinnacle of the king of the animals, the sort of pinnacle of existence, God's creation, or sort of in more of an atheist perspective, sort of the one most dominant species, sort of that perspective, which many of us do not share now, but that perspective is sort of biologically ingrained in us is this sort of mathematical greatness, and sort of the problem with that is a lot of it is sort of more coincidence. I mean, obviously, I don't think Africa. I mean, Africa, it's a continent. It's not being designed according to the golden ratio. For the pyramids, I think the actual ratio of the base length to the height is more like 1.571, and so I think a lot of people, it's like, well, if it's close to 1.6, then it has to be the golden ratio, right? But as we've just sort of discussed, the golden ratio is the most irrational number. So even if you were to say 1.6 or 1.618, that's really not it. You can't really quantify it. You can sort of give as many decimal places as you want, and we kind of each, we'll sort of understand what you mean, but for the most accurate, it's just writing, okay, well, phi. Like, phi, we understand what that means. Sort of like you just write pi. And so, again, there's sort of and then, another common sort of application of this spiral is something that we'll cover in just a little bit, is sort of in the Fibonacci sequence, that numbers petals on flowers will occur in Fibonacci numbers. However, again, looking at data, actually the number of flowers that follow this pattern is roughly equivalent to the numbers that don't. So there's not necessarily universal sort of law necessarily ingrained in plant biology that says you must have this number of petals based on this formula. Interesting though, in terms of how some flowers actually sort of place their seeds, if they're sort of if you're rotating around a point or placing seeds. I think the image that might come to mind is like the sunflower head, and actually the most efficient space-wise is going to be where essentially every 0.6180339 of a turn, you are putting a seed, so you have the least amount of wasted space. And there's a great great video by Numberphile on this one. I will include a link to that if you want to sort of explore that side of it as well. But again, there is so much that's actually cool and unique to the golden ratio that there sort of are these more popularizing ideas. That may not necessarily be true, but it doesn't dampen its beauty. So what I think we will do next is sort of mention this idea of the Fibonacci sequence, sure lots of you've heard of that, may even know what it is, but I think there's some pretty cool stuff in there as well. So why don't we move on to that? And so, the name Fibonacci is coming from, I think, roughly 16th century Italy, and obviously by person named Fibonacci, right? I don't think his name is actually Fibonacci, but sort of that's again the sort of Renaissance, time of rebirth, re-exploration. But actually, there's an Indian mathematician who lived roughly the 2nd, 3rd century BCE. Who actually had discovered this sequence. So what we know is the Fibonacci sequence. He also had discovered binary numbers. And I think something perhaps like Pascal's triangle. So this guy, Pingala, Indian mathematician, roughly 2nd, 3rd century BCE, incredible mathematician, and sort of did a lot of mathematics that sort of then the West sort of quote discovered much later. But so the credit obviously we now know by Fibonacci, but actually Pingala did discover the sequence known today as a Fibonacci sequence much earlier. So this was roughly, if Fibonacci was, roughly like the 16th century, several thousand years earlier. So it's kind of cool to keep the historical perspective in mind. That people actually knew about this, people have known about this sequence for thousands of years. And even more interesting things like binary numbers and Pascal's triangle. So, have actually, we've sort of known this for quite some time, and I think it's a testament to, our human ingenuity, regardless of, whomever discovered it. It doesn't change its beauty, nor its importance. And so, okay, without further ado, moving from the historical perspective, apparently DSLR cameras have a 30-minute limit, so I finished the video and I realized, the camera didn't work, so I have to redo this. Okay, well, anyways, as I was saying, the Pingala-Fibonacci sequence is going to be 0, 0, 0, essentially infinite zeros, and then a 1. And then a 1, 2, 3, 5, 8, 13, 21, 34, 55, etc., 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 going on forever. And I think this is just a brilliant metaphor for our universe, because essentially we just have nothingness, right? Just 0 after 0 after 0, nothing, nothing, nothing. And then all of a sudden, with this burst of light, this burst of energy, suddenly this whole system, this whole dynamic, beautiful system comes alive, right? Sort of this Big Bang moment starting with this little one, but growing sort of like Gödel's recurrent loops, just infinitely out. It's mesmerizingly beautiful. I think just sort of even as beautiful, perhaps not even more beautiful than the golden spiral. Okay, but now let's say I want to be able to find the nth Fibonacci number. I want essentially to find a function that'll sort of allow me to express this. Well, as many of you know, right, sort of if I just ignore this part, and just look here, I know that essentially I know I start with 0 if n equals 0, and I know I'm 1 if n equals 1. Otherwise, I'm going to be the previous Fibonacci number plus the second previous Fibonacci number if n is greater than or equal to 2. So in other words, I start with 0 and a 1. Then this 1, right, is going to be defined as the sum of the previous two. So 1 plus 0 gives me 1. And I can carry this on infinitely, right? So this is what we call a recursive definition of a function corresponding to the Fibonacci sequence, the Pingala-Fibonacci sequence. Okay, but what if I don't want to write out a sequence? What if I want to ask you, what is the 100th number of the Fibonacci sequence, without creating the sequence before it? Just what's the nth? I want immediately, right? Okay. Okay, but you know, if someone just asked you, find the nth number of the Fibonacci sequence, you might just be inclined, okay, well, I'll just write out the sequence and go until I reach n, the desired n. However, I don't think it's very illuminating. I mean, it gets the job done, but it's sort of, there's more to math. There's more to our humanity than sort of getting things done. More to life, right? Okay. So what if I then want to, excuse me, I want to find an expression for the nth Fibonacci number. And to that, my dear friends, we will turn to linear algebra, the language of linear algebra and matrices and dimensions and vector spaces, all kinds of wonderful things. Okay, so, in other words, let's say if I just write this sequence up here again for our benefit. Oops. 1, 2, 5, 8, 13, 21, 34, 55. On and on and on. Let's say I have a vector, call it v naught. And I want v naught to be a 2 by 1 vector holding the first two numbers of the sequence. So 0 and 1. Let's say I want then v1 to hold 1 and 1. v2 to hold 1 and 2. Up. Vn, I want to hold the nth Fibonacci number in the first row, first column position, and then in the second row, first column position, the nth plus 1 Fibonacci number. And right, so if I had 0 and 1, well, this 0 is the nth, right? So this would be n equals 0, n equals 1, etc., etc. So I have 0 and 1, right? 0, 1. Then this 1, right? This nth plus 1 Fibonacci number is going to become the nth Fibonacci number of the next vector. And then this nth plus 1 is going to be the sum of these two. 0 plus 1 is going to give me 1. So this is the idea. I have these, okay, I'm taking these vectors which are defined as matrices, right? I'm using the language of matrices because linear algebra is all about matrices. And they're incredibly cool. And we'll see why. So let's say I want a matrix, call it A. I want to say I have a matrix A, such that when I take A times Vn, I'm going to get Vn plus 1. Essentially, I want to create a matrix that's going to model this Fibonacci sequence in terms of transforming one vector into the next. So by the laws of matrix multiplication, I know it has to be a 2 by 2 matrix in order that when I dot that, I multiply it with Vn, which is a 2 by 1 matrix, with the nth Fibonacci number, and then the nth plus 1 Fibonacci number in the second row position. And I know I need this to give me the nth plus 1 Fibonacci number, and then the nth plus 2 Fibonacci number, which is really going to be the sum of Fn and Fn plus 1, because remember, no, let me fix that bracket. The sum any Fibonacci number we defined in our recursive definition is just the previous 2. So if I'm n plus 2, that's going to be n plus 1 plus just n, right? So, okay, I need a matrix that satisfies this expression. Well, okay, I know that I need to multiply something, laws of matrix multiplication. I take this row, I spin it by 90 degrees, multiply it by this vector. I know that, well, this term needs to go to 0, but I need this. I just need that nth plus 1. But then likewise, I need the sum, I need both of them. So you can verify, if I take this row, spin it by 90 degrees, multiply it by this column vector, 0, 1, I'm going to get Fn plus 1. Take these guys, spin them, I'm going to get Fn plus 1 plus, or Fn plus Fn plus 1. And this is going to give me, indeed, the nth plus 1 Fibonacci number corresponding to the Fibonacci vector. So, hallelujah, okay, this is good, right? We have our matrix A. Okay. Now here's the problem. Or not a problem, but here's the thing. Here's the deal. We know that, based on this definition, A times V naught is going to give us V1, right? If I take this matrix, multiply it by 0, 1, that's going to give me 1, and then 0, 1, right? 1, 0 times 1, 0, 1 times 1 is 1. So that's going, so this is the, I know that this works. I can prove them for the other ones. But okay, I need to find Vn, because I need this guy. I need to find Fn. I need to find the nth, an expression, excuse me, for the nth Fibonacci number. Let me take a quick drink. And so, essentially I know what I can do is if A times V naught is really V1, right? If this is V1, then I can multiply this guy by A again to get V2. And I can continuously multiply by A's to get our Vn. So, okay, all you're saying is I need A to the n V naught is going to give me Vn. No problem, right? Piece of cake. Okay, well, there's a catch. Unfortunately in life, there's always a catch, right? This matrix is not a very good boy. It's not particularly easy to deal with because, well, I mean, if you're on your own, try finding this to the n, right? Well, okay, you can maybe square this guy pretty easily, but try, tripling it, quadrupling it, quintupling it, sextupling it, etc., etc. It starts getting out of hand. How do you, again, you can do it on a calculator, but by hand, you don't want to multiply n of those guys. It's not fun. So how do we get around that? Is this just throw in the towel? Is this just the end of the road? No, of course not. It's always another way, always a way. Life shall find a way. And here it is. We can find the way using something called an eigenvector. And I think that Tony Stark in the Marvel movie Infinity War used eigenvalues and eigenvectors to sort of reverse the Thanos death snap, whatever. Spoiler alert. So obviously probably not mathematically accurate. I haven't actually seen that movie in a while, so I have to tell you. But it's there's some but Marvel aside, eigenvectors are actually incredibly useful in terms of basically modeling what happens to data after you do a ton of transformations. Sort of what sort of are the general trends. So really, really important in data analysis and principal component analysis, all kinds of stuff like that. Okay, so what is an eigenvector? What is it, right? Okay. Well, an eigenvector is a little thing we define by this equation, where x cannot equal 0. So in other words, we have a matrix equation, A times x, where x is not just a variable, but like we had before, it's a column vector, matrix of unknowns. And then, so that is our eigenvector. And this is our eigenvalue, this lambda. It's just a scalar. You could have whatever placeholding value you want. But the idea is, so I take A, multiply it by some x, and I'm going to get essentially a scaled version of x, right? Some lambda, some scalar value times x is what I'm going to get essentially by this multiplication. And the reason that I say I want solely non-trivial solutions, in other words, I don't want x equals 0, because if x equals 0, this is a pretty boring problem, because a times 0 is 0. Remember, where this is really the 0th vector, technically. It's like a matrix of zeros. A times the 0th vector is just going to give me 0. And any scalar times the 0th vector is just going to give me 0. So I have 0 equals 0 forever and ever and ever, and that's boring. Boring because it's pointless. I can choose any eigenvalue, and it just perpetually 0, and that's boring. Okay. So that's why we specify x cannot be equal to 0, because we want a non-trivial solution. We want to find eigenvalues that work. Okay, so what we can do is I can move this to one side of the equation and get this. Now, okay, so this I is called the identity matrix, and essentially what this is a matrix that along the diagonals, main diagonal is a 1, or 1s, and then everywhere else are just zeros. 0, 0, 0, 0, 0, 0. So essentially I just it's an n by n matrix going on, and definitely with the idea that essentially, right, this is sort of our multiplicative inverse, because if I take it, identity, rather, if I take, x, I'm going to get x, right? If I were just saying, if I had 1 times y equals y, where this is just regular algebra, you'd agree that 1 times anything is going to just give me that same thing. It's not going to change the values, because it's essentially our multiplicative identity. It's not changing anything. And so, likewise, in linear algebra land, we have some important parallels, some analogs with regular algebra. Mainly, one of those is multiplicative identity, right? This idea of, essentially think of I as a 1. Don't be too stressed. Okay, so we want to solve this equation. How do we even begin to do that, right? I mean, okay, well, one thing we can do is say, okay, what happens if this guy was invertible? And now you may be saying, what's invertible? Well, imagine if I had some expression, xy equals, 3. If y is invertible, then I could say x equals 3 over y. Again, where y cannot equal 0. So in other words, if I have 1 over y equals y inverse, and this exists, then y is invertible. In other words, I can take its inverse. So essentially, I can multiply both sides of the equation by y inverse. And I get this. So, likewise, in linear algebra, if this matrix, A minus lambda I, is invertible, then I could take A minus lambda I inverse, multiply it by both sides of the equation, I know that this is just going to go to 0, And I know this, right, if I had y times 1 over y, if I multiply any matrix by its inverse, if its inverse exists, I'm just going to get the identity matrix, right? Essentially just going to get 1. It's just going to cancel, basically. That's sort of the beauty of it. If this existed then, I would get x equals 0. But I've already said up here, x cannot be 0. I need a non-trivial solution. So what I can conclude then from this is that a minus lambda I cannot be invertible. It can't be invertible, otherwise I can multiply by its inverse by both sides of the equation, get x equals 0, and then everybody's sad because we haven't accomplished anything. So if a minus lambda I cannot be invertible, well, what does that mean? If I had a matrix A that, say, was invertible, what I can do is I can express A as the product of what are called elementary matrices. And what an elementary matrix is, essentially, is I have I'm performing some transformation on the identity matrix, and we're successively going this way, successively to transform the identity matrix, remember, just the matrix of all ones along the diagonal, into whatever my matrix A is. So, for example, if I had some A or some E, EJ or whatever, that was 2, 0, 0, 1, then essentially I'm taking whatever's in the x direction, I'm stretching it by a factor of 2. So if I have like a normal unit square or something, now it has a base of 2 and a height of 1. So now it's like a unit rectangle. Or, for example, if I had like a 1 and a 2, then I have like a shear where I just take my rectangle or my unit square and I shift it over, like shear it over like this, where this length is 2. So what's really cool about matrices, and actually the whole reason why we define matrix multiplication the way we do, is such that when we multiply matrices, we are essentially performing linear transformations. So anytime we talk about transforming one function to another, or going from one vector space to another vector space, doing some operations, whatever, we're using matrices. That's why we use matrices. That's why we use the language of linear algebra, because it's so convenient for expressing linear transformations. So, and an important property is if I can express A essentially as some series of multiplication of these various elementary matrices, because they're composed of what are called elementary row operations, performing these various changes to our identity matrix, which would in this case just be 1, 0, 0, 1. So what's important to note is that these elementary matrices will always have a non-zero determinant. And the determinant, to be really quick, is essentially it's a scalar value that's going to give the sum of all of the signed elementary products. So in other words, the determinant of this guy would be 1 minus 0, so just 1. Because essentially I know that it's going to be AD, so 1 times 1 minus BC, 2 times 0, which just gives me 1. So in other words, if we are invertible, then the determinant of A cannot be 0. Because these, since I can write A as a product of these matrices, none of these matrices will have a determinant of 0. There's no way I can get 0 without multiplying by 0, because I'm multiplying, right? So in other words, if it's not invertible, the determinant is 0. And this is what we can use to find our eigenvalues and our corresponding eigenvectors. And if this is kind of going fast, I have to have to beat the clock, but basically, the idea is, okay, what I can do is, so I know that my matrix A was A was 0, 1, 1, 1. Essentially, what I can do is if I subtract lambda times the identity, what I'm going to get is a negative lambda, 1, 1, 1 minus lambda. And if I find the determinant of this, or find when the determinant of this is equal to 0, I can just sort of solve that. So I have negative lambda times 1 minus lambda minus 1, right? AG minus BC for a 2 by 2 matrix. Not too bad to find the determinant. Well, I know this is going to give me a quadratic, by the looks of it, lambda squared minus lambda minus 1. And if you're not excited, I don't know, you've been saving because this is our friend. This is our good old pal. We've seen this guy 3 times now, right? Lambda squared minus 1 minus, or lambda squared minus lambda minus 1. We know this guy. We know that lambda has to equal 1 plus or minus square root of 5 over 2, the golden number. I'm sort of jumping with excitement because we're making progress. We are seeing this interesting connection develop between the Fibonacci sequence, right, which you kind of already saw with the Sectio Aurea, and the golden number. And so for just simplicity's sake, we'll go ahead and say, so we know we have two eigenvalues, 1 plus square root of 5, so, and 1 minus square root of 5 over 2. So I'm going to just say that this is equal to v. V just some constant, right? And I'm going to say that I know that then 1 minus square root of 5 over 2 is going to be 1 minus v, because if I add these two, I'm going to get 1. And I know that if I add these two guys, I'm just going to get 2 over 2, which is 1. So those are my two eigen values. And then what I can do essentially is find the corresponding eigenvectors. So I know that if my lambda is v, well, this is going to be negative v, 1, 1, 1 minus v. And essentially, I find the null space. I need to find the null space of this vector, or this matrix. In other words, find where this equals 0. I can do that by multiplying by this vector, imaginary vector AB, find that equals 0. And what I can do is create a system of equations and simplify them. And what I will get is that the eigenspace, and okay, now there's an eigen thing, right? The space, don't be concerned about that. Essentially, if I had a matrix like 1, 0, that was sort of defined as a member of R2, then R2 is just the vector space, the place upon which the vector is defined. So don't worry about it too much. I consider this eigenspace, I know, is the span, all the linear combinations of the vector that should be 1 minus v, negative 1 minus v, and 1. And so this, for our purposes, will be our eigenvector. Just this guy. But in theory, we can have any scalar multiple of this eigenvector will also be an eigenvector defined for the eigenvalue of lambda equals v. So, but we'll just pick that eigenvector. It doesn't matter. We just need a eigenvector corresponding to this eigenvalue. Now, if we put in the other eigenvalue, what we'll get is a negative 1 minus v, 1, 1 minus 1 minus v. And again, we essentially solve for when this, we find the null space, find basically when this goes to 0. And what we find is that the eigenspace of this guy and all the linear combinations, so really the scalar multiples, of the of the vector negative v1, where this is again our eigenvector, defined for the eigenvalue of 1 minus v. Okay, so what's the point? I think you have to, and so I'm going to actually just be right back, restart the video. Okay, so now essentially, what can we do with this information? How does this help us in any way? Well, if I have a matrix, call it D. If this matrix, if a matrix D exists such that it is the product of P inverse AP, what essentially I'm going to get is that this is going to mean that D and A are similar matrices, meaning D and A are similar. They are really good matrices, because what this means is that A and D are going to have the same eigenvectors, they're essentially going to represent the same transformation, but in a different vector space. And so what we essentially want is to have a matrix defined over an eigenspace. So essentially that we essentially have a nice matrix to multiply. And because we know that we call it D because it's going to be a diagonal matrix based on what we choose P inverse and P to be. So essentially, if what this is going to give us, and I'll just write it here, we can say A is going to be P D P inverse. So we can perform those operations on this matrix equation based on the rules of matrix multiplication, because I'm essentially I know that P is invertible, so I need to just find a P, and that's why we went through the trouble of finding the eigenvectors, because I can say P is going to be a matrix that contains the eigenvectors. So to the negative 1 minus v, 1, to the negative v and 1 would be P. And now to find the inverse of P, what I can essentially do is what's called row reduced echelon form. We call it RREF. I can reduce this guy to get to basically its component, to its sort of just most basic parts, and then like we did with the eigenvectors, to find the eigenvectors by finding the null space, I essentially can just get a system of, it just simplifies the work to get a system of equations, which I can then basically use and create these these products of elementary matrices that give us P, and then I can take the inverse of those, right, and get P inverse. It's sort of, remember we talked about, when you're writing a matrix that's invertible in terms of elementary matrices. So the idea being, there are different ways we can do this. We can use a calculator, or do it by hand, but the idea is saves the time. What we'll get is this matrix, 1 over the square root of 5 times 1, both these are 1, and then we end up with v, and then negative 1 minus v. And essentially, we know that A, right, A is just going to be 0, 1, 1, 1. We know that if we take P inverse times A times P, what we're going to get is a D matrix that's diagonal, meaning it's only going to have numbers along its main diagonal. And we know we have 2 eigenvectors, 2 by 2 matrix. What it's going to be is it's going to contain the eigenvalues corresponding to the eigenvectors that we had in P. So this eigenvector, negative 1 minus v1, right, this corresponds to the eigenvector of v. And then this guy, the negative v1, corresponds to an eigenvector of 1 minus v. So essentially, this is our matrix D, and hence D diagonal, because the only values exist are those along the main diagonal. These are zeros. And the point to this? Well, D is an incredibly friendly matrix. We love the matrix D because D to the n is just going to be b to the n 1 minus v to the n. Those zeros are going to stay zeros, and so it's really easy to find this matrix, to find d to the n. It's hard to find a to the n. A to the n is just cantankerous, troublesome. It's not willing to easily yield its secrets. Whereas this D is much more amenable to our quest in this pursuit of Fibonacci. So, what we can do is, but because we know that A is P D P inverse, I can say A to the n is P D to the n P inverse. And we don't need to worry about those P inverses. They're essentially just going to cancel. So this is the expression for A to the n. And we've been looking for A to the n because we know that if we have A to the n multiplied by V naught, we're going to get Vn. We're going to get this guy, which is going to give us the nth Fibonacci, the expression for the nth Fibonacci number. And then we also have the nth plus 1, but we don't really care about that. We want the nth. And so, essentially, we are basically there. What we can do is calculate what a to the n is by taking p dn p inverse. Multiply that by v naught, and we know v naught is just going to be 0, 1, and we'll get our Vn. And so to kind of just spare the pain and agony of calculating, sort of, you can calculate that on your own, but essentially, right, I can just sort of say, okay, well, we know that a to the n times v naught equals Vn, and therefore, where a to the n is p d to the n p inverse, and therefore, v to the n is going to give us this matrix, right, which we know is going to be the nth Fibonacci number, nth plus 1. And I can say that the nth Fibonacci number is going to be given by the expression, okay, 1 over the square root of 5 times v to the n minus 1 minus v to the n. Or if we go ahead and substitute 1 over the square root of 5 times 1 plus the square root of 5 over 2 raised to the power of n minus 1 minus the square root of 5 over 2 raised to the n, end bracket. But boom, this is that which we have been seeking. An expression for the nth term of the Fibonacci sequence. It does not rely on recursion in its definition. Right? You can pick any n and you will get the sequence. Or you will get, better yet, the exact number. The exact Fibonacci number corresponding to the n. So if we were to try it, for example, n equals 1, you would have, well, this would just be, 2 root 5 over 2, that just gives us root 5, 1 over root 5, cancels, just gives us 1. And indeed, so we know that when n is 1, this indeed works. And so what I think is even more brilliant, though, is that this expression for the nth Fibonacci number uses the golden number, because this number, our phi was 1 plus or minus square root of 5 over 2. And this is that one. This is 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. So, intricately interwoven into the heart of the Fibonacci sequence, clearly, is the golden ratio, the golden number. And two, if we were to look at, we would take the numbers of the Fibonacci sequence and start and take the ratio of them, going, okay, 1 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, 13 over 8, etc., etc., etc. I don't know if you can see this might be cut off. Essentially is approaching phi. It's sort of going like this, sort of oscillating, essentially going to this asymptote that is phi, that is this 1.61803398878, etc., 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 right? And so I think it's just a neat, fabulous way of encapsulating the integral relationship between the golden number and the Fibonacci sequence. And we saw that again with sort of the looking geometrically at Euclid's geometry problem, getting the golden rectangle, Sectio Aurea, doing a proporzione, and then sort of taking that and creating a spiral where essentially you get squares that correspond to Fibonacci numbers, going up in the Fibonacci sequence, and you get the golden spiral or the Fibonacci spiral, right? And so it's just, let me check the time. Good, okay. It's fabulous. It's just elegant, it's beautiful. It's amazing too. You put in any n integer, again we're assuming n is an integer because we're sort of defining each term, such like that. That you get all integer numbers, even though you have some root 5s in there, right? And again, we've said that these technically golden numbers, right? Both of them, are the most irrational numbers that exist, sort of in this more abstract, number theory land. And so it's just fascinating that's such infinite beauty we can represent, with such precision, and above all, such elegance, and so again, I think if you just sort of use a recursive definition, sure, you can do that. You can get the Fibonacci sequence, find, stop at whatever nth term you're at, but really looking closer at at the relationship between the values and using linear algebra to help us, we get a pretty interesting picture of the full extent of not even the full, but just a greater extent of the importance, the significance of the golden number. And so, even if, say, the Greeks didn't, construct the Parthenon to adhere to the golden ratio, and perhaps, if, unfortunately, my face is not perfectly, correlated to the golden spiral, the Fibonacci, sequence, it doesn't mean that this number isn't incredibly beautiful, incredibly useful. Everything from the way that flowers do actually, it's sort of the most efficient way of having sort of seeds, right? Being the most rational number is a pretty amazing honor, I think. And it's a phenomenal number, phenomenal equation, and even if it's not the secret to life, it's still a very central number, and it definitely sheds light on the fact that our universe, there is mathematics present. It's not all just necessarily made up. It corresponds to what we see sort of in the real world, and we can harness that. That's sort of a testament to our abilities as a species to harness the infinite and express that, and make that definite, make that known, as sort of a statement of our existence, an assertion of meaning and purpose. So I think definitely intriguing philosophical implications as well. And so, well, that has been quite an amazing long journey. Now I know those dang DSLR cameras have a 30-minute video recording limit. Why on earth would they do that, right? It's just frustrating. It's just stopping us from having longer conversations, right? But anyways, you know, I hope that in light of everything that's going on, you stay safe, stay happy, stay healthy, do lots of math during your quarantine time. You know, as always, have a math-tastical holiday season, and have fun.